All right, folks, let's get started here in a new chapter. Section 12.1, we're going to look at parametric equations. And this is one of my favorite scenarios to introduce the power of parametric equations. Say we have a small rocket and it's launched from a table. The table's 3.36 feet above the ground. The initial velocity of the rocket is 64 feet per second, and it's launched at an angle of 30 degrees with respect to the ground. So given that information, we know the rocket will travel along a parabolic path, and the parabolic path that the rocket will travel along is given by that rectangular equation. Now, the rectangular equation, it does a good job of telling us where the rocket has been. In other words, if we graph the rectangular equation in the viewing window, x min 0, x max 140, y min 0, and a y max of 30, we'd get the following graph. All right. If we think of x as being the horizontal distance that the rocket would be from the table, and y is the vertical distance that the rocket is above the ground, then the rectangular equation, it just simply tells us where the rocket has been. So let's look at the graph one more time. So any point on that curve tells us the x-coordinate of the point would tell us how far away from the table the rocket is horizontally. The y-coordinate would tell us the rocket's height above the ground. However, the rectangular equation does not tell us when the rocket was at any point xy. So in order to answer the when question, what we do is we introduce a third variable that I'll call t, and this third variable is generically called a parameter. Now I would use t here because I want it to represent time. But in general, I could introduce any variable I want. That variable I'm introducing is called a parameter. So when I introduce this third variable t, it allows us to write x and y, the horizontal distance from the table, the vertical distance above the ground. It allows us to write those two as functions of t, which is kind of cool. So for this rocket, it would give the following, what are called parametric equations. X is 32 square root 3 t, and y is negative 16t squared plus 32t plus 3.36. Now with these parametric equations, we can now tell where and when for the rocket. So for example, at t equals 0, so at t equals 0, we know the rocket hasn't been launched yet. That's the initial value for t, the initial time. At t equals 0, well, if you substitute t in, if you substitute 0 in for the t's in the parametric equations, you would get x is 0 and y is 3.36. That's its initial starting point. Before it's been launched, it is 0 feet horizontally away from the table, because it's on the table, and it's 3.36 feet above the ground, because the table itself was 3.36 feet tall. So with those parametric equations, if I want to know where the rocket is at, say, 1 second, I would put 1 in for the t's, and that would tell me exactly where the rocket is. It would tell me how far horizontally it's away from the table, and it would tell me the height above the ground. So what we're going to do next, I'm saying, grab your calculator for what we're going to do next, because I'm going to show you how to graph parametric equations and everything involved when you do graph parametric equations. So get your calculator. All right, it's time for me to call up my calculator. And when I call up my calculator, I'm going to go over how to get your calculator in parametric mode, everything involved with what's called the viewing window, the graph, and what needs to be drawn on the graph that the calculator doesn't do. So when you put the graph on paper, what you would need to add. So let me call up my calculator. Let's see. All right, here it is. So first, let's put the calculator in parametric mode. So I hit mode, and let's see, I come down. There's parametric. So I go over and I hit enter. So now my calculator's in parametric mode, and I want to graph the parametric equations that models this rocket. So I hit y equals. Let me clear this stuff out of here. So first thing, notice when you hit the y equals, notice there's an x sub 1 and a y sub 1. That's because in parametric equations, you need something for x and you need something for y. So let's see, x was 32 square root 3 t. Now, folks, your variable button, when you hit the variable button when you're, graphing, functions, like y equals x squared plus 1, your variable button was the variable x. When you're in parametric mode, this variable button is now a t button. So I just have to hit it. See, there's a t. And see, y was negative 16 t squared plus 32t plus 3.36. All right. So next, I wanted to show you everything about the viewing window. Okay, you now have something new in your viewing window. You have a t-min, a t-max, and a t-step. I'm going to make my t-min 0 since my parameter t here is representing time. Negative value of t would imply time travel. I can't do that yet. I'm going to make my t max 5. And then t step. The t step is, and I'm going to go old school on you. Back when I was learning about parametric equations, I had to make a table of values. So I had to pick different values of t and the corresponding x's and y's and plot points. So t-step, that's kind of like the increment I would have used in my table of values for t. So if I were doing this by hand, I might look at t values of 0, 1, 2, 3, 4, etc. In my table, doing it by hands, the t-step would be 1. But since I have a graphic calculator now, and it can calculate things a lot more quickly and efficiently than me, I'm not going to let it off easy and just do a t-step of 1, where it would start at 0 and then 1, and then the next t would be 2, etc. I'm going to make my t-step, 0.1. And that's already in there, but let me type it again. Let's see, now the y-axis. Well, I had already graphed this in rectangular coordinates, and I think I said the x-min was 0, and the x-max was 140. I'll scale my x-axis by 14s. And I think I also said the y-min was 0, the y-max was 30, and I'm just going to scale that by 3s. So now I'm ready to look at the graph. Now when I click graph, you have to really watch how it's graphed. Well, that was really quick. But it was graphed in this manner. Let me do that again slowly with my cursor. That's the one thing that's not shown on the calculator that we will need to, and I'll show you on the board. When we put this graph down, we have to put arrows on the graph to show this was the order in which the graph was traced out. So I'll show you that on the board. One more thing that I'd like to show you here is if you activate the trace button, Notice at trace, you now have a value for t, x, and y. So let's say I am curious to know where was the rocket after 1 second. So I hit 1, and it's telling me at 1 second, it's 55.425626 feet horizontally away from the table, and it's 19.36 feet above the ground. So that parametric equations, those parametric equations answers 2 questions. It answers when and where. So let me head off to the chalkboard here real quick and put this graph on the chalkboard to show you exactly what it should look like when you put it on paper. All right, folks, for that rocket example we were looking at, I said I would show you something at the board that the calculator doesn't do for you, but you have to do when you put your graph on paper, in general. So this is true for graphing any parametric equations. And it's called the orientation of the graph. So how was the graph traced out? So when we graphed this is the graph of the parametric equations for that rocket. It was graphed in this orientation. That's how it was traced out. So all we have to do is you just put little arrows on the graph itself. Those arrows show the orientation of the curve. So that's the one thing we have to add. We're going to be using our calculator to get the graphs of these parametric equations, but we must always put in the orientation. So that's it. Let's head back to the slides now. All right, now we've seen our introduction to parametric equations. Next up is the following definition. If f and g are continuous functions of t on an interval I, then x equals f of t, y equals g of t. Those are called parametric equations, and t is simply called the parameter. The set of points x, y you get as t varies in the interval I, well, that's just the graph of the parametric equations. Now, the parametric equations and the graph produce what is called a plane curve, and in math we kind of denote that with an uppercase C. So that's the definition of parametric equations. So let's do an example here. Sketch the curve given by x equals t squared plus t and y equals t squared minus t on the interval where t goes from -3 to 3 inclusively. So you know what? I'm not going to head off to the board to do anything here. I'm just going to call up my calculator and do the graph. So let's see. Y equals, okay, let me clear that. X is t squared plus t. And y is t squared minus t. Okay, now I do have to fix my viewing window because, I was told t goes from -3 to 3. So I'm told my t min is -3. My t max is +3. I'll leave the t step at 0.1. Let's see, x min. Oh boy, I don't know what to make my x min. I'm making a guess here. I'm gonna make it a -2. X max. Well, I'm kind of looking at my x. X is t squared plus t. Let's see, if I put a t value of 3 in there, I'd get 9 plus 3, which is 12. I'm going to go a little larger than 12. I'm just going to go to 14. And then I'd scale my x-axis by 1s. Let's see, a y minimum. I think y's there could be some negative values for y, not too negative, so I'm guessing a -2. And let's see, y maximum. Well, if t has a value of -3, -3 squared minus -3 would be 12. I'm going to go a little larger than that. So folks, I'm going to scale my y-axis by 1s. This is just my good first guess at what the x and y's should be. So let me look at the graph and see how it's traced out. So it looks like that was the orientation. Notice it definitely has a beginning point and an ending point, and that's because t was just on the interval -3 to 3. So when I put this graph on paper, you know, I would have a dot here, a filled in circle, and I would have a dot here. I would graph this and then put those arrows like I showed you earlier to indicate the orientation, to indicate how it was graphed. So that's the basics of doing a graph. So let me continue on here with the slides, because what we're going to do next, and it's going to be in the next example, it'll be part B of the next example. We're going to show how, if you're given a set of parametric equations, how to eliminate the parameter and therefore determine the rectangular equation for the curve. So we're going to look at this example. X is 3 minus 2t, and y is 2 plus 3t. Part A, I say sketch the curve. Part B, write a rectangular equation for the curve. So you know what? One more time, let me call up my calculator. And let's sketch the curve. So let's see, y is 3 minus 2t, and y is 2 plus 3t. So x is 3 minus 2t, y is 2 plus 3t. And then for my, my viewing window, well, let's see, I'm not given an interval for t. So I guess t is allowed to go from -infinity to infinity. I'm going to make my t min -5 and my t max 5. T step of 0.1 is good. X min, oh, I don't know. I'll just go -8 to 8. And I'll make my y min also -8 and y max 8. So now I'm going to look at the graph. And so that's what I need to graph. So you know what? When I head off to the board here to do part B, I'll put the graph on the board and, you know, the arrows that showed the orientation. So I'm getting ready to head off to the board, mainly to do part B of this example. So let's go to the board to do that. All right, this example, we were given the parametric equations, x equals 3 minus 2t and y equals 2 plus 3t. In part A, we were asked to sketch the curve. Then in part B, we're asked to write a rectangular equation for the curve. So we're going to eliminate the parameter in our set of parametric equations and come up with a rectangular equation, an equation just involving x's and y's. So on the slide, I'd already called up my calculator to look at the graph, and remember what I told you, I have to put the graph down. I saw what the calculator showed me, but then I have to put the arrows to show the orientation of the graph, to show how it was traced out on the calculator screen. So part B, eliminating the parameter. So for this one in particular, I noticed that my x looks kind of linear and my y also looks kind of linear. So what I could do is I could pick either one. I could pick x equals 3 minus 2t, or I could pick the y equals 2 plus 3t and solve for t. So if I solve this for t, I would subtract 3 from both sides and then divide both sides by -2 to give me that. And actually, I would rewrite this. Instead of the negative in the denominator, I would move it to the numerator, and I would look at it as being 3 minus x over positive 2. Or over here, I could solve for t, and that would give me a y minus 2 over 3 is equal to t. So once I solve for t, I could take this, and I could substitute it into my x equals equation. I could substitute that in here for t. Or when I solve for t here, I could take this and I could toss it in here for t. It doesn't matter which way I go on this one problem. That's why I showed both. I personally would take 3 minus x over 2 and toss it in here for t, because this is already in a very user-friendly form. So I put 3 minus x over 2, put it in here for t. It's in a very user-friendly form. If I wanted to use my calculator in rectangular mode, if I wanted to use my calculator to graph this, it's already in the y equals form. And that's it. That's a rectangular equation for this set of parametric equations. So to practice this eliminating a parameter, I'd like you to pause the video, go to the section 12.1 exercises, try number 17, and then you know the drill. Once you're done with number 17, restart the video. I'll be here at the board cranking through it. Hi folks, you have x equals square root t plus 4, y equals 3 square root t, and t's on the interval 0 to 16. That's what number 17 was. And in part A, you were asked to eliminate the parameter to get a rectangular equation. I can see a couple of ways to get started here. But I'm just going to focus on what jumps out at me the most direct way. If I know x equals square root t plus 4, then I know x minus 4 is the square root of t. So I can take x minus 4, toss it right in there for the square root of t, to immediately get y equals 3 times x minus 4, or y equals 3x minus 12. That was pretty friendly, but I am going to make a special note here. Notice that t was on the interval 0 to 16. So if t is on the interval 0 to 16, look at what my x is. X is square root t plus 4. So if t is 0, x would be 4. If t is 16, x would be, well, square root 16 plus 4. That's going to give me an 8. So I'm looking at this rectangular equation on the interval where x goes only from 4 to 8. Because on the t interval, 0 to 16, x can't take on any other values. X is always going to be somewhere between 4 and 8. Likewise, on this interval, I could say my y's for the rectangular equation. The y's are going to be between, 0? Yeah, that's 0. Put 16 in here, and 12. I'm going to use that information because, I'm getting ready to head back to the slides to do part B. Because part B, I'm going to call up my calculator. I'm going to call up my calculator to get the graph. But this is going to be something, kind of important for me to know, to keep to keep an eye on. And when I go back to the slides and call up my calculator, I am going to get something that looks like this. So let's head back to the slides. I'll call up my calculator and we'll do this graph. All right, folks. So, we looked at how to eliminate the parameter. Number 17 gave you a little bit more practice. But I did say for us, when you did number 17, I did say, when I came back here, I was going to call up the calculator, to look at the graph. So, let me do that. And let's see. X was the square root of t plus 4. And y was it was just 3 times square root t. Okay, and wait, we were told the window, t goes from 0 to 16. And in my analysis, we determined that on the window, when t goes from 0 to 16, x's would be on the interval 4 to 8. So I'm going to make my x min, I'm going to make it 2, and I'll make my x max 10. And I also showed that the y's went from 0 to 12. So I'll make my y min -2 and my y max 14. Notice I always give myself just a little bit of a wiggle room. So now let's look at the graph. So that's the graph of the parametric equations. And notice this is also the graph of the rectangular equation we came up with, y equals 3x minus 12, where x is restricted to go from 4 to 8. So x goes from 4 to 8. And the y's are going from 0 to a y value of 12. All right, so that was the graph. And continuing on, we have another example. So for each set of parametric equations, first thing, sketch the curve. The second thing, write a rectangular equation. Part A is x equals t squared minus 1 and y equals t cubed minus t. And in part B, x equals 3 sine theta minus 1 and y equals 2 cosine theta plus 2. So, I tell you what, folks, I'm going to let you do the graph for part A. I'm going to let you do it on your own. When I head off to the board, I will put what the graph is up on the board. But I will do the graph here for part B. So let me call up my calculator again. Let me move it over here so we can see. So here's the deal, folks. Your parameter doesn't always have to be a t. Here the parameter is theta. But when I use my calculator, when I'm in parametric mode, the calculator in parametric mode considers the parameter to always be t. So if I want to graph this, I need to graph 3 sine t minus 1 and y equals 2 cosine t plus 2. Notice we are told the parameter goes from 0 to 2 pi. So I better have my parameter go from 0 to 2 pi. And now once I get this to play the game, I'm going to make my t step now. I'm going to make my t step pi divided by 32. Really make the calculator work. Okay, x min. I'm not exactly sure. I think I'm just going to go -4. And I'll make my x max positive 4. My y min, I think -5 should be sufficient. And a y max of 5 should be sufficient. I'll scale by 1s. So here comes the graph. Oh, wait, I have an error. What did I do? Oh, yeah, look at that. I got ahead of myself. The x scale is 1. My y min is -5. My y max is 5. Calculator didn't like that. Neither would I. So here comes the graph. So it looks like the graph was traced out in that orientation. When I do part B at the board, I will put the graph up there again. I just wanted to show you that the parameter, so what if in the book they give you the parameter as being theta? It's a set of parametric equations. X equals something, Y equals something. You can replace that theta with a T because it's parametric equations. But that graph to me looks like an ellipse. So when we get the rectangular coordinate, the rectangular equation, I'll be curious to see if we get something that reminds us of an ellipse. So I'm going to head off to the board now to do both parts A and part B. And the big thing here is, we are going to be focused on, really how do we write a rectangular equation? So eliminating the parameter. So here we go, off to the chalkboard. All right, folks, in part A of this example, you were given the parametric equations x equals t squared minus 1 and y equals t cubed minus t. In part 1, you were asked to sketch the curve. Then part 2, come up with a rectangular equation. So eliminate the parameter. So part A, when I do part A, when I graph on my calculator, I get something like this with the arrows. I think I kind of had to zoom in a little bit in the area around the origin to really see that nicely. Let's talk about getting a rectangular equation. Okay, now this one isn't quite as straightforward. One thing that jumps out immediately at me is my y is a t cubed minus t. I could factor out a t, and that leaves me with t times t squared minus 1. Now I think I am getting somewhere because here's a t squared minus 1, and I know t squared minus 1 is x. So just kind of looking ahead a little bit, I know that is x. But I can't have y equals t times x. That is not a rectangular equation. A rectangular equation will just have x's and y's in it, not a third variable. It's not going to have the parameter t cruising around. So, if we know x is t squared minus 1, don't we also know that x plus 1 is t squared? So if I look at this rectangular, or if I look at this piece of my parametric equations, factoring out the t, if I square both sides, I get y squared equals t squared times t squared minus 1 quantity squared. Then I think I am almost done. T squared, well, that's x plus 1. T squared minus 1. Well, we know t squared minus 1 is x. So I put x in there. That is the rectangular equation. I have nothing but y's. I have nothing but x's. So that's the rectangular equation. There was a part B. So let me get the board erased because part B's kind of interesting because we're now looking at dealing with some trig equations, which I know that had you all excited. So you were given in part B, x is 3 sine theta minus 1. Y is 2 cosine theta plus 2. And theta is on the interval 0 to 2 pi. I believe we already looked at the graph for this, and let me just stress again. I stressed this when making the graph. The parameter doesn't always have to be t. Yeah, the majority of the time, the overwhelming majority of the time, the parameter is going to be t. But in this set of parametric equations, the parameter is theta. So what? It's not a big deal. And we saw to use the calculator. I just had to say, you know what? I'm going to replace the theta with t. It's the exact same thing. So on the calculator, we graphed x equals 3 sine t minus 1, and y was 2 cosine t plus 1. We made our t min 0, our t max 2 pi, and we should have seen, I don't know, it looks something like that. I believe that was the orientation. And I think I told you, it kind of looks like an ellipse. Well, let's see. Let's do part 2 here. Let's eliminate the parameter. So, well, you know what? Look at the x equals 3 sine theta minus 1. I can add 1 to both sides, and then divide both sides by 3 to get that. X plus 1 over 3 is sine theta. Here I could subtract 2 from both sides, and then divide both sides by 2 to get y minus 2 over 2 is equal to cosine theta. And I remember an identity that says, a Pythagorean identity, that says sine squared theta plus cosine squared theta equals 1. Well, if I know sine theta is x plus 1 over 3, let's put it in here for sine theta. So we have x plus 1 over 3 squared. Cosine theta is y minus 2 over 2. Put it in there. Y minus 2 over 2. That's a rectangular equation. It's got x's and y's. Kind of cool. We got to use a trig identity, a Pythagorean identity. You know, I would probably look at this as x plus 1 quantity squared over 9 plus a y minus 2 quantity squared over 4 equals 1. And I do remember from college algebra, I do remember this is a form of an equation that represents an ellipse. The ellipse has a center at negative 1, 2. That doesn't look too bad. My drawing looks like it might be at negative 1, 2. That's 9 is 3 squared, 4 is b squared. So I'm kind of remembering some stuff about ellipses. That's the rectangular form for an ellipse. But notice in eliminating the parameter, we went back to one of the most basic trig identities to help us. So give you a little bit more practice here on just eliminating the parameter. And section 12.1, the exercises. I'd like you to do number 19, part A. That's just eliminating the parameter. So pause the video, go do 19A. When you're done, restart the video. We'll see if you have it correct. All right, in 19A, you were given x equals 3 cosine t and y equals 3 sine t. Eliminate the parameter, get a rectangular equation. And hopefully you were pretty dialed in and you immediately looked at this and said, well, x over 3 is cosine t. And here you said y over 3 is sine t. You said, hey, I know a Pythagorean identity. Cosine squared t plus sine squared t equals 1. So you put x over 3 in for the cosine t. Y over 3 in for the sine t. And, you know, this is just x squared over 9. And this is y squared over 9. Or you could maybe look at that as x squared plus y squared equals 9, which tells me when you graph this set of parametric equations on your calculator in parametric mode, you better see the graph of a circle centered at the origin with a radius of 3. So hopefully that was it, and hopefully you got it, and let's head back to the slides and see what is next. All right, in that last example, I hope you were able in part A to get the, a good looking graph using your calculator. I did put it on the board. We saw, we had to be a little clever in part A to eliminate the parameter. Part B came back to an old trig identity in eliminating the parameter. And hopefully in 19A, eliminating the parameter, you handled that pretty quickly. So that's the basics, introduction to parametric equations. Now it's time for us to do some calculus of parametrics. So here's our big theorem. If you have a smooth curve C or a plane curve C, and it's given by the equations x equals f of t, y equals g of t, parametric equations, then the slope of the curve at the point xy is given by dy dx. dy dx gives us the slope. When we have parametric equations, dy dx will equal dy dt over dx dt, provided, of course, dx dt does not equal 0. Folks, for some unknown reason, your book does not mention how to find second derivatives in the parametric world. I don't know why, but we're going to talk about how you get second derivatives in the parametric world. So right now I'm going to head off to the chalkboard to discuss how we would get a second derivative in the parametric world. And I'm going to make use of this theorem here. So hopefully you have this written down on your notes, because I'm heading off to the chalkboard to discuss second derivatives in the parametric world. All right, so here we're going to try to make some sense out of how to get a second derivative. I don't know why the book doesn't discuss this, but that's what we're going to do right now. So our theorem said the slope is dy dx is dy dt over dx dt. So dy dx, or another name for it, is y prime. First, notice it's going to be a function of t. So the derivative, dy dx, is going to be a function of t. So to get the second derivative, you have to differentiate the first derivative, but the first derivative is a function of t. So that means you have to d dt the first derivative, which I can write this as dy prime over dt. And then I'm going to say, well, dy prime over dt is dy prime over dx times dx dt. So here's where we're at. Progress check. We have dy prime over dt is dy prime over dx times dx dt. So now if I pull this up here, going to give me some space, pull it on up there, I can look at this, and as long as my dx dt does not equal 0, I can divide both sides of this equation by dx dt. So that's what I'm going to do. I'm going to pull it on up here, dividing both sides of the equation by dx dt, and that gives me dy prime dt over dx dt. Well, that's dy prime dx. All right, so since we have dy prime dx is dy prime dt over dx dt, look back that dy prime dt is really just d dt of y prime. So I'm just gonna write that in over there. I'm just gonna substitute that in. So I'm just gonna substitute in dy dt, or dy prime dt, dy prime dt, it's just this. So I'm just going to substitute that in. It's d dt of y prime, and that's over dx dt. But d dt of y prime, d dt of y prime, well, y prime is dy dx. Y prime is dy. Remember, it's just another way to say dy dx. So let me put this in here for y prime. So let's look at what that really says. Oh, wait. I have typo. That's d dt. Sorry. You saw my typo at the board. So let's look at what this is really saying. This is really saying you differentiate with respect to t, dy dx. This is dy dx, the first derivative. You differentiate it with respect to t, because that's all you can do. It's going to be a function of t. And you divide that by dx dt. And when you do that, it gives you dy prime of x, but dy prime of x, I mean, think, that's d dxing y prime. You're differentiating a derivative. This is just funnier notation for the second derivative. So let me write the second derivative notation as that. So that's how we compute a second derivative. So I'm going to cut to the chase on how to compute a second derivative. I wanted to give some explanation rather than just saying this is what you do. This is all the explanation for this is what you do to get a second derivative. You have your first derivative. Your first derivative will be a function of t. d dt, the first derivative, and that's all over whatever dx dt is. So let's head back to the slides. We're going to do a couple of examples practicing getting derivatives and second derivatives. And you'll see it's not that bad at all. In fact, it's pretty friendly. All right, since we've seen how to do second derivatives in the parametric world, and we have that theorem showing us how to do dy dx, let's crank through an example where we're going to determine dy dx and the second derivative. And in part A, we're going to do x equals 6t squared and y equals t cubed. That's the set of parametric equations. Then in part B, our parametric equations are x equals 1 minus cosine t and y equals 2 plus 3 sine t, as long as t does not take on a value, an integer multiple of pi. That's why we have t does not equal n times pi. So let's head off to the chalkboard and do a little calculus of parametrics. All right, folks, in this example, we're asked to determine dy dx and the second derivative for, in part A, the parametric equations x equals 6t squared and y equals t cubed. Then in part B, x equals 1 minus cosine t and y equals 2 plus 3 sine t, as long as t does not equal n times pi, as long as t is not an integer multiple of pi. So let's get started. First, here's what you really need to know. This is what you need to remember. This is going to be important in a couple of sections when we start to talk about polar coordinates and calculus and polar coordinates. And that is that derivative dy dx is dy dt over dx dt. So here's y. Y equals t cubed. dy dt is 3t squared. It's just the derivative. Here's x. dx dt is 12t. That just, well, look, we could simplify that down. That's 1/4. That's t. So that simplifies down to just a 1/4 t. See, that's not bad. And as I said, the derivative is a function of t. So to get the second derivative, you have to differentiate with respect to t the first derivative. And then that's all over dx dt. So your first derivative is a function of t. Differentiate that. d dt, that the derivative of 1/4 t is just 1/4. And then that's over dx dt. Well, dx dt is still the same. It's a 12t. And I should clean that up. Complex fractions, not good. The second derivative is 1 over a 48t. So I told you this wouldn't be bad, getting the derivative and getting the second derivative. So, yeah, I tell you what, going to do something a little different here. There's part B. I want you to do part B right now. So go ahead, pause the video, do part B. Once you finish part B, restart the video, and I'll be here at the board to work through it. All right, part B, derivative. So you should have written down the derivative, dy dx. It's dy dt over dx dt. So dy dt, all right, so the derivative of 2 plus 3 sine t, that's, 3 cosine t? And then dx dt, see the derivative of cosine is negative sine minus a negative, so that's just sine t. And because I'm going to get the second derivative, I would write that as 3 cotangent t. Because, so that's the first derivative. Because when I'm getting the second derivative, notice the first derivative is a function of t. So I have to d dt, the first derivative. And then that's all over dx dt. So let's see, the derivative of cotangent. Derivative of cotangent is negative cosecant squared. So we get negative 3 cosecant squared t. And that's all over dx dt. Well, dx dt is sine t. And you know what? I can rewrite this because I know sine. Sine is the reciprocal, sine and cosecant are reciprocals of each other. So sine, cosecant are reciprocals of each other. So I can write this 1 over sine t as a cosecant t and simplify the second derivative down to just a negative 3 cosecant cubed t. Not too bad getting derivatives and second derivatives. So let's head back to the slides and see what do we have in store next. All right, hopefully you saw that wasn't too bad and you saw what the big deal is in getting the second derivative. When getting the second derivative, our first derivative is a function of t. So that's why we have to d dt that function of t, and then it's over dx dt as we saw earlier. When I turned you loose on number 5, when I turned you loose on part B, hopefully you're able to get it. But let's move on to the next example. Now that we know how to find derivatives, let's find the equation of the tangent line. Tangent to x equals 3t and y equals 8t cubed. So it's tangent to the curve given by that set of parametric equations. And it's tangent at a t value of negative 1/2. So I'm going to head off to the chalkboard and crank through this example. Then I'll probably have you do a problem, make sure you get it correct. But before I go to the chalkboard, one thing I wanted to mention about this section. I'm asking you all on your own to read page 762. There's a discussion about arc length in the parametric world, and there's a couple of examples there. You're gonna need to read that. It's going to be helpful for you when you try to do exercises 81 through 87 odd. So make that note. There's something in the book I'm asking you to read on your own. But let's head off to the board now and let's get an equation of a tangent line. All right, in this example, we're asked to come up with an equation of the tangent line, tangent to the curve given by the parametric equations, x equals 3t and y equals 8t cubed, at t equals -1/2. So we know we need a slope. In order to get the tangent line, we need to know the slope of the tangent line, and we need to know the point of tangency. That's actually the first thing I determine, the point of tangency. Since I am told t is -1/2, t is -1/2 tells me exactly what point we are at. Put -1/2 in here for t, and you get 3 times -1/2, that's -3/2. So the x is -3/2. Put -1/2 in here for t. So -1/2 cubed, that's -1/8. 8 times -1/8 is -1. So I have my point of tangency. I just need to get the slope of the tangent line. And what tells us slope of the tangent line? dy dx. So dy dx is dy dt over dx dt. dy dt is 24t squared. dx dt is, well, just 3. So that simplifies down to 8t squared. So at t equals -1/2, dy dx has the value of finding, putting -1/2 in there for t. That tells you the value of dy dx at t equals -1/2. So -1/2 comes in here for t. -1/2 squared is 1/4. 8 times 1/4, 2. That is the slope of the tangent line. The slope of the tangent line at that point. We know the slope. We know the point. See, we know point, we know slope, we know point, slope. To get the equation, I would use the point-slope form. So I have a y minus -1. That's y plus 1 equals the slope, which is 2, times x minus -3/2. That's an equation. That's a good equation for the tangent line. But I might at least distribute the 2. And then I could subtract the 1. You know. But this would have been a good equation for the tangent line as well. So folks, to practice this, getting an equation of a tangent line, I would like you to try in section 12.1. Right now I'd like you to try in the exercises number 76. So you know the drill. Pause the video, do number 76, restart the video. I'll be cranking through it. All right, folks, number 76, you were asked to find the equation of a tangent line to the curve given by x equals e to the t, y equals natural log of t plus 1, at t equals 0. So, equation of a tangent line, we need to know the slope of the tangent line, we need to know the point of tangency. I'm going to start at the point of tangency again. T equals 0, well that can tell me exactly what point I'm at. So if t is 0, I come back here, Put 0 in for t. E to the 0 is 1, so x is 1. My y, well, I put 0 in here for t, so we get the natural log of 1. The natural log of 1, well, the natural log of 1 is 0. So folks, we have our point of tangency. All we need is the slope of the tangent line. And remember, slope of a tangent line is given by dy dx, which in the parametric world, that's dy dt over dx dt. Alright, so dy dt, the derivative of natural log is 1 over the t plus 1, and then would be times 1. Remember the chain rule? The derivative of what's inside, that's just 1. Over dx dt. Well, derivative of e to the t is e to the t. So we have dy dx is 1 over e to the t times t plus 1. So folks, at t equals 0, dy dx is equal to 1 over e to the 0 times 0 plus 1. So that's 1 over 1. And that's the slope of the tangent line. So we know the slope. We have the point slope. Use the point slope formula. Whoops. So we have y minus 0 equals the slope m times x minus 1. Y equals x minus 1. That's it. That's the equation of the tangent line. Now I did mention it on the slide before we came here to the chalkboard to do this example, but I'm going to mention it one more time. You need to read in the book on page 762, you need to read about arc length, how to find arc length if you're given parametric equations. And I think I've assigned maybe 4 exercises, 81, 83, 85, 87, where you're finding arc length. So you'll need the information that's on page 762. But that's it for this section on parametric equations. Now you're ready to go do the exercises in section 12.1. Thanks for watching.